So thank you, Dr. Bartolev. Thank you, everyone, and thank you to the UK Foreign and Commonwealth Office for this invitation to this meeting. So the title of my talk, of course, New Ways of Seeing the Earth from Space with the European Sentinel satellite. So my name's on the screen. I've got some business cards with me. Happy to talk with people today, also tomorrow. So a number of affiliations. I'm within the Centre for Landscape and Climate Research. This has been led up by my colleague, Professor Heike Bautzer. We're part of a wider Leicester Institute for Space and Earth Observation. Within the University of Leicester, of course, Leicester's very famous for a couple of things. The football club, of course, who's currently second in the Premiership and won the title a few years ago, but also another thing that Leicester might be famous for, we found the last King of England to die in battle was discovered under a car park, and that was quite a important. We're very central in the UK, just 1 hour north of London, so invitations to visit can be made here and now. So very fond memories of past visit to Russia. 20 years ago, I came to Moscow, spent a few days in the capital city here, because I'd read in a guidebook that on the streets of Moscow you could buy beer for about 10 pence, which is like a dime, and I couldn't believe it, but so I had to visit the city to discover that that was actually true, and it was, and I managed to I spent £1 buying 10 bottles of beer from the streets and walking around Red Square, and then we got the flew to Krasnoyarsk, and then we got the Trans-Siberian train from Krasnoyarsk to Irkutsk, and spent a number of days in and around Lake Baikal. And what was that to do? That was to map Russian forests using a satellite where we had to get the receiving station into Ulaanbaatar to download the radar data from the European Space Agency, and combine that with radar data from the Japanese Space Agency to produce a map and work with Russian foresters with their forest inventory that contains many variables to work out which one of those variables was most related to the signal from the satellite data, and that was growing stock volume. And growing stock volume, from the talks already this morning, seems to be important. And what Dr. Bartolev was saying are challenges still today about mapping the status, the extent, the species of Russian forests, even though we've made great advances in observations. Now, I was invited here as part of a science and innovation network, and maybe we're talking a little about the science today, but also we need to think about the innovations that we make. And I think part of where my research interests sit are trying to be innovative around the use of space-based data, satellite Earth observation data. I think what characterises University of Leicester, perhaps different to other institutions in the UK, is that we'll try and tackle a problem by thinking about solutions from thermal, optical, microwave, LiDAR, and potentially use all those together. And I think that's what's really powerful today. And the innovation might come with using cloud-based services. The innovation might come from integration of different data sets, because it looks like we're in a position where we're collecting more data than we're able to kind of process sensibly. And that's starting to open up real debates in the university, cross-discipline activity around machine learning with computer scientists. And this seems to be like a holy grail. Now the term that we're hearing a lot about is artificial intelligence and remote sensing. And so what I want to try and do is to really, I'm here as a kind of salesperson to try and sell these new group, let's say, of European satellites. And what I'm interested in, what Dr. Bartolev said, he's producing a map of forest cover using MODIS. Now, what if MODIS stops working tomorrow? MODIS has given great service to the scientific community. Is he going to use VIIRS? Are we ready to step into the Landsat scale type of large area processing? Can we now use Sentinel-3 instead of MODIS? And how seamless might that transition be? Will we have to do something to manage the biases? That's the kind of things that we're interested in at Leicester. And although my research has taken me away from working to some extent specifically in Russia, it might be the right time, because it sounds like the science questions are really contemporary, valid, impactful, to try and think about using some of the tools and processes that we've been developing to tackle some of these questions. So one of our projects that we've been working on, this is a project funded by the European Space Agency. Now, I'm delighted to tell everyone that our relationship with the European Space Agency won't change with Brexit, so we can celebrate that. And one of our issues is mapping small fire burn scars. It may not be such an issue in Russia, but where the fire size tends to be quite large, but that's probably a characteristic of the boreal forest. We might get smaller fires within tundra, we may get agricultural fires, or this relationship between agriculture and more natural vegetation. But the current crop of satellites observing on a global daily basis simply can't characterize a small fire. So if we're trying to get the emissions right, then we need to look at alternatives. And one of those alternatives is looking at radar data. But we didn't just use backscatter, which is your kind of standard product from Sentinel-1. We decided to see if we can use interferometric SAR coherence. So radar has the advantage, of course, of seeing through clouds, but it's very sensitive to moisture. But it's also sensitive to changes of the scatterers, the above-ground biomass. And what we're interested in is what happens to that when it's been affected by fire. Because some fires burn through the canopy, some fires are ground-based and leave the leaves that then eventually fall off. There's all different fire kind of processes. And part of us we were interested in, now we've got Sentinel-1, what can we do with this satellite? And these are my colleagues. Cloud covers are of considerable importance, because to see burned areas, we clearly need to see the surface, and in some cases, the longer we leave the surface without an observation, the less chance we might, our certainty around characterising that as a fire disturbance might be lowered. Again, some fires in the boreal forest leave fire scars there for a long time, but other fires might not. And the fires might also be quite small. And we can see here, there's, in this context of Africa, there are a number of places where we might not see the surface sufficiently with optical data than we might with radar data. On the right is the distribution of burned area. On the left is the mean cloud cover. We worked out what the likelihood of observations that we might see from Sentinel-2. And Sentinel-2, medium resolution optical instrument, is a much more advanced revisit overpass time than Landsat, 6 days between Sentinel-2A and 2B. But even in those conditions, the cloud cover may be restrictive. Why do we use coherence? Because people have used backscatter data to look at soil moisture and look at forest properties. We saw an example of the glob biomass product. Now we had a chance from Sentinel-1, a C-band radar with a 6-day repeat, which is much better than the 35-day repeat we previously had, to generate systematically coherence. What is coherence? It uses the phase signal. It's the correlation of the phase. So if a structure hasn't moved, and that means in the wind, so structures like buildings and houses, they're very stable. Their phase characterization contains lots of signal and not noise, and that phase is preserved. So if we have water, that decorrelates almost instantaneously, and over forest, the kind of phase decorrelation is very much related to the above ground biomass, and so on. It's a bit more interesting than radar backscatter. It doesn't suffer from the same problems as speckle or topographic challenges. But what we wanted to do was, we know how to generate this coherence from a pair of images. Can we do it over a very large area over a whole year, where we can build a system that can pick and choose the right image pairs? Because we require 2 images, the coherence is an indicator of the correlation between the phase of those 2 images. So we'd have an observation here, 6 days later. 6 days later, there might be a gap, and 12 days to the next observation. So I see coherence as an indicator of the stability of the surface. Now, under a fire process, your surface may be stable. Then over a period of time, it might decorrelate as you go from forest to some other kind of surface, and then it might become stable again. So a way that you might look over a time series for spectral change, we could look over a line. So there's, I hope maybe the slides can be distributed. I'm very happy for these to be distributed to everyone, because it kind of gives you an overview of the kind of processing that we had to go through using Snap Toolbox, but also there are some tools. I think there's a tool called SNAPU, which enables you to do the coherence mapping, which doesn't sit automatically within Snap. We had to look at automatically going through all the Sentinel hub, and I think we use the Alaskan SAR facility. Isn't that a bizarre thing, where to get European satellite data, we use an Alaskan SAR facility to automatically source the images that we need. And we generated large data sets as well. So again, it's a grand challenge to make sure, as a community, we can access high-performance computing. The raw satellite data with the backscatter coefficient, we're not using just the intensity, so we've got to use the single look complex data, and we've got to process that, multi-look it, resample it. Luckily, these things are fairly automated these days in Snap. Look at a multi-temporal speckle filter if we're doing the backscatter, and then try and parallelize this processing on our HPC, because what the area we're interested in is the whole of sub-Saharan Africa over a year. So, and this is why I think this could be interesting in a Russian context. So, when we look at coherence, our coherence value scales between 0 and 1, where 1, which doesn't really exist in images, but a value that's heading towards 1 shows very, very stable phase correlation. So I always interpret that as being urban structures, roads. It doesn't matter whether it scatters strongly or scatters weakly, it's that stability. A value that heading towards 0 is definitely water, and in between is this transition of what I would interpret as how much of the ground is visible versus how much vegetation there might be in the way. So a grass surface will have a fairly high coherence. A forested surface with no gaps will probably have towards a low coherence. So we generated these coherence values here at our test site in Africa, and we've got values up to 0.7 over there. But we're looking at a time series. So we're not just assessing the behavior of the coherence, we're looking at how it changes over time. And then we can generate these RGB kind of stacks using three image dates. And then we can start to look at the relationship between, because we simply didn't know how does the coherence behave after a fire. So here's a fire, here's the kind of visible Sentinel-2 image. You can see the edge of the fire scar here. And we can look here, and the behavior of that fire scar, high coherence in some areas, in the RGB timescale, but the colour here is indicative of either low coherence becoming high over either one or two of those dates. So that told us there is a signal, or there seems to be a signal in the coherence related to a fire. Then we had to kind of think about the kind of how would we take this time series and try and make sense of it and try and classify. This is a burned area, because that's what people want to know. We have a strong, with this particular ESA, European Space Agency project, Climate Change Initiative, the relationship with users is absolutely there. So they're very insistent on having a burned area map, then a not burned area map, and an unknown, and also an uncertainty layer, which I think is related to the standard deviations, and then we also have a land cover map underneath it. So the coherence between images spanning the burned area seems to be low. That would make sense. But also if the type of burn, because if you have trees, if the trees fall over, then suddenly that you might go from a fairly highly coherent surface to still a coherent surface, because the trees it's been such a severe fire that the trees have fallen over. So there's potentially all sorts of kind of sub-question analysis that can be performed on this kind of data. But importantly, we could see the actual fire taking place. So this is going to kind of go through a time series. So where we might see solid white here, this would indicate high coherence, and I think that's the situation after the fires really impacted the surface. So what we also notice, compared to the optical data, you see a burn scar and the surface is black because of the ash on the surface, and maybe the leaves have been consumed, so the near-infrared has dropped. Maybe it takes a bit more time from how the radar sees it for that burned area to be confirmed. So if a user is interested in the absolute date of burn, then we think that the actual classification from the coherence might not be interesting. But what I want to point out is the colours. These aren't clouds, of course, but this is now going into the wet season. So what we also get, I think we can see is this interplay between moisture, vegetation moisture, soil moisture, the wet season, the dry season, the fires, the drying out of the vegetation, a very dynamic landscape, and being revealed through simply these RGB triples. Now, I don't know what it would be like to observe over a year a time series of coherent changes over the Russian forests, or this zone where the tree line is. Possibly what you're seeing is also kind of melting of and behaviour of the soil surface and the water surface as well. So that would be an interesting thing to experiment with. So what did we agree? This is a map that says the red is where we agreed in the burned area, because we did a Sentinel-1, Sentinel-2 comparison, so radar to optical. We agreed on unburned. Of course, most of the tile is unburned. But some areas where Sentinel-2 detected and Sentinel-1 didn't. And that's part of the research programme, to understand why that is and look at improvements. And then there's a few areas where we detect. The Sentinel-2 unburned, the Sentinel-1 burned is a bit more easy to explain through cloud. The Sentinel-2 not seeing the surface. But why Sentinel-2 sometimes sees it and Sentinel-1 does not, I think it's because of the type of fire possibly, the lag between when the optical data sees it and because maybe the comparison has to work within certain dates. And we had a slight improvement in the emission error when we adjusted the dates. If we took into account a slight offset between when the Sentinel-1 might see it and the Sentinel-2, then we will get a better agreement. And I think that's really interesting, that the effects of fire, we've seen this in our projects in Indonesia, where we've systematically every year detected the burned area, and particularly its relationship with burn depth and potential emissions. And that's been verified with some airborne LiDAR data. What we're seeing is areas that are affected by multiple fires, the kind of impacts are different. Normally there's lesser impact with repeat fire. But also the fire, true fire impacts may not be felt on an area for at least 2 or 3 months afterwards, when maybe the trees start dying and so on. So maybe the Sentinel-1 is a bit more informative about post-fire recovery and process, but that's a question for another day. And you can see when Sentinel-1 versus Sentinel-2 detection date, keep in mind they're both overpassing nominally every 6 days, sometimes every 12 days. That's quite a difference. And this is great by using Sentinel-1 and Sentinel-2. The processes are completely different. Spectrally, top of leaf, with radar, penetration through the canopy to some extent, and looking at the distribution of the scatterers after the fire event has happened. And there's models to help with both. Sometimes we use this MIMICS, a microwave canopy scattering model, to help to explain what we might see. And it's very complicated to parameterize a burned area forest landscape using a radar model, because people don't have the field data to support it. And another great link to Russian colleagues here. So I'm the kind of developer of the Copernicus Global Land Service, and back in 2001, Dmitry Ershov, who's in the audience here, he contributed an algorithm to map Russian fires, and this was the first attempt at a global burned area map by piecing together the jigsaws. We had one algorithm from Canada, we had, I think, one from Russia, we had one from Mozambique, we had 3 from Australia. There was a big fight in Australia, but of course, why not? Because the fires today in Australia are completely devastating, and certainly lessons to learn there. And then when we put this jigsaw together, actually no one was looking at Brazil. Again, another really interesting fire-affected landscape. And we did a piece of work, as just an aside, we did a piece of work from this project to look back at the fire history of Brazil. And in fact, what we discovered this year was quite an exceptional year, but 2 years ago was also an exceptional year in Brazil. And by the way, just across the border in Bolivia, it was pretty bad as well there. So by having these long-term data sets, we can start to look at some of the behavior, notwithstanding errors and uncertainty, of fire-disturbed areas. So coming back to the story, there's these big gaps in our global product, and I said to my colleagues at the Joint Research Centre in Italy, we can't produce a global algorithm where most of South America's missing, most bits of Mexico, India, China. I said, it doesn't look very global to me. And he said, well, find out which algorithm works okay in these other places. And I tested the one from Dimitri, and his did a reasonable job in most of these other fire-prone areas, which is really anywhere in the world. So that has evolved through Spot VGT, to Proba V, to 300 meters, to now our latest contract is to move it to Sentinel-3. Because this word service is very important, that's part of the innovation. Now we've created a service, what do we do if Sentinel-3 fails? Well, luckily the Sentinel program is supposed to outlast most things, and by having a continuity program, and that's really good for us to now start thinking about how we can piece together time series data. So there's a little bit of Russia in this Copernicus program, and there's other global burn area products, of course, the MODIS, and now we're getting one from the Climate Change Initiative program, and that's also excellent, because we need better algorithms, we need more intelligent algorithms to do. But we can also use hotspot, and it's a shame my colleague, Professor Martin Wooster, is not here, because he's an expert on active fires and using fire-rative power or energy to characterize the intensity and the biomass consumed, and he's doing that in many places around the world. But we can use the hotspot to tell us where to look for a burn, and we can then look for a change. But look at this optical data globally at quite coarse resolution. It's very noisy. So there's a lot of effort in Europe to really try and work on denoising some of these time series data. And I think that's where we can be really innovative. If we can help the user to correct for some of the directional effects, to do good cloud masking, you do cloud and cloud shadow screening, getting that out to other users can actually, we're part of a story that can help solve some big problems. So this transition, we're spending a lot of time thinking about the next generation of satellites. And I think a long time ago we used to use some Russian data, but we don't hear too much about Russian data sets. I'm trying my best to use Chinese data. When I work with my colleagues, they tell me about Gaofen, but I say, where's the data? And they say, well, it's there somewhere, and let's try and use it. But that's a long time series process. So I'm really interested, if we are to develop a network, how we can integrate satellite data sets, because we think we can do it. Because we can now look at different spectral wavelengths, how they fit together. There's some clever tools to integrate those. So at least we can remove some of the bias in this effort. And clearly the move to Sentinel-3 is very exciting with the SLSTR and also the ULTRI. So we look forward to that. Another thing we're really trying to do is push out tools that can facilitate the comparison between products. We want to put as much information in front of the users, climate modelers, who want different things, landscape modelers, dynamic vegetation modelers, and sometimes they don't really know which product to choose. In fact, they may be fed up of reading the format and the algorithm definition. So what we might want to do is to think about how we can push out some of these products on the using these kind of web mapping tools. And if you've got a Gmail account, and these slides can be distributed, if you click on this, you'll see some of the kind of coding work that we're doing to try and display our global map, burned area map for a number of years, against the MODIS map, and maybe against some regional maps. Because the power of, I think, Google Earth Engine is we can just keep pulling in data as long as it's registered. And people can then look at that for their region of interest and say, actually, this product looks like it's ideal. It's at the right spatial resolution. So with a Gmail account, you can click on this and do some exploring. The challenge for us is to get multiple years on there, coded nicely and scaled nicely, and so it actually can see the imagery against the backdrop of Landsat data. So we can compare for those months where the burned area says it's a burn with the Landsat image before and after that time period that's relatively cloud-free, and making that, as soon as the user clicks on it, doing all that backroom processing so their visual experience makes them think, yes, I like satellite data, I want to use that product. This is the period that we're working in. We've also put a great effort on validation, and we're interested in potential future collaborations in this area. If we're to validate a global burned area product, and you can make a proxy for even Russia, it's such a vast land area, is how do you go about validating that? When actually you probably don't really believe the field data statistics. And you've got, and maybe the fires where the field data, where someone walks around and collects the perimeter, particularly in Europe, they're biased towards fires that mainly towards an urban area, because there's implications for compensation and insurance, and they want to be really sure what's been affected by a fire or not. So we put a great effort into coming up with a stratification for global burned area detection, how we sample, how many samples we need, making sure we're sampling low fire frequency areas, otherwise we'd be introducing a bias there, how we systematically do that from the source of data, Landsat initially and now Sentinel-2, because we want to compare 300-meter global burned area data produced on a daily basis with Landsat images every 16 days, and part of them potentially cloudy. So we built a framework. Because, I mean, look at that. That is your burned area. And this is Africa. This is really complicated, and that's our digitizing. So we employed students, and this is what's great in a university. Plenty of students there to do some project work, but really they're a source of relatively free labour, of course, but it's all good for their development. And so we're digitizing away, and we did a multi-year, looked at all the biomes, looked at where they're stratified by where actually the hotspot data was. So that tells us where the fires are. That really helped with the stratification. So we did 1,200 sampling units, 100 Landsat image pairs, digitized them before and after. So we worked out, actually, this is where Stephen Stamen, I think, is a statistician from New York. He said, actually, if you only do this subsample of a Landsat tile, it's representative of the Landsat tile. We thought, oh, goodness, it just saved us a load of work. Because we were trying to digitize the whole of the Landsat tile. I said, no. In fact, with Landsat 7 as well, just go for the bit in the middle without all these gap problems. And he proved it, that if we chose that subsection as our reference image, as long as we took into account the biomes and the distribution, and we did 100 per year. So we've now got a multi-year global burned area reference data set. And I'm willing to bet, as you can see, there's quite a few sitting in Russia. But we need to carry that on. Our funding's run out. The Copernicus service demands it. And we now need to work out how we're going to produce these additional data sets. Instead of an image pair, for Africa, we did a long time series validation stack. This really helped us with our you may detect it on a burned area, but can you, over different vegetation conditions of the surface, as you go from a wet season to a dry season, is your validation at that moment in time representative of the burned areas across that time season? And if, as Dr. Bartolev pointed out, at the beginning of his analysis, the fires were taking place at the beginning of the season compared to the end of the season, we could actually think about validating that those area estimates are right across the whole of that area. So we've had some real fun trying to work these Landsat images. This was the work on the sample allocation. We published this, if you get in touch we can send you the references, but we had to publish the sample methodology before people would actually believe that the validation metrics that we produced are valid. We came up with a number of metrics, dice coefficient. I think the issue is the proportion of burned area across the whole Landsat scene is very small. So our detection of a non-burned area, there's much more land area, much more likely that would take place. So we came up with, as well as your kind of standard commission emission, we looked at this dice coefficient that gave you an indicator. I think it was a coefficient in the balance of errors between the two burned and not burned characteristics. And we could then look at the performance of each algorithm or approach in terms of the dice coefficient across the different areas, and also look at any relative bias. So what we've started to build now, and this is part of the CEOS land product validation working group, is a data set of validation where if someone builds a large area algorithm and it meets the criteria in terms of daily updates and things like that, we can offer some validation data, which is the methodology been published and adopted by the LPV community. And that's really important. Sometimes validation is the last thing to think about after the budget's probably run out. And then because we've got yearly data, we can look at the behaviour. Because, of course, you want a product which is where the accuracies of the year-to-year performance are stable. Okay, if it's very bad, at least you know it's bad every year. That's one way of thinking about it. But also, you might want to think about whether there's a kind of, this might be your first indicator that the sensor is on decline, or there's a problems with some of the spectral bands, and so on. But we didn't detect in any of the data sets. We evaluated a lot of data sets, even the MODIS MCD64, a global burn area product, and we didn't see any of those. So we've got a test bed now for evaluating the performance, and we've got an intercomparison framework so we can give some pointers to algorithm developers about where their algorithms may or may not be performing. And of course, Dimitri's is always the best, of course, naturally. Actually, what we can say is, it depends if you're interested. If you do not care about fire detection time, so really, the day of burn is not important. All you want is over a fire season, you want to know how much is burned. Then our colleagues' work, we worked on Sentinel-1, but the Sentinel-2 is the best, followed by this fire CCI, then the MODIS, sorry for the acronyms. If you care about the timing of a fire, then the MODIS MCD64. Why does that work best? Because that is seeded by an active fire detection, which is very, very accurate in the temporal domain, because it's a very strong thermal signal. And what I also pointed out here, we've done now the prototyping work to go from MODIS scale burn area detection to Sentinel-2. And that, thinking about the processing, we've lost the daily resolution. We've gone to 6 to 12 days, but we've gone from 300 meters minimum to something like 20 meters. And now I think we're at that point where we can start processing large data sets, and that's where I guess this helps. And we can see here, you can see the jump in resolution here. This is fire CCI, this is probably MODIS 500 meters, same as MCD64. The official MODIS product, and this is the Sentinel-2. This is Landsat. This is, and it gives you an indication of the jump in resolution, the detail of the fire mapping. Now, what would be interesting, clearly not every fire in Russia is massive. There may be some small fires which may be burned for a short amount of time, and maybe jumping to Sentinel-2 will help. One quick section, as we reflect on the opportunities to network. This is a networking opportunity. I started working with China 5 years ago. One of the things we have with the UK and China, we have a joint UK-China space workshop, and it may be something for people here to think about, where sometimes we go to Shanghai or Beijing, and at other times delegates from China come to UK, and it's supported by both governments, and it kind of forces us together. We even signed some MOUs, which I don't even tell my university about in case they say you can't sign MOUs, but I like signing MOUs. It's an expression of intent to collaborate. And so 5 years ago this happened, and now we're starting only now to see the benefits, and the benefits of that collaboration is that I can visit China. In fact, I'm doing 20, 25 days a year there, but they're also visiting UK, and we're also getting some of their hard-working PhD and master's students to spend up to 3 months in our lab, doing their projects and doing their research, but interacting with us. And I think that's a really, thinking about ways of collaborating together, getting people to spend more than just 3 days, which is what it is this time, working with each other. What we're trying to do is to, again, they have a complete reliance on MODIS data. And we're thinking, well, let's try working with some European satellite data just to see if it actually adds value or integrate between the two data sets. So this is my colleague, Darren Gent. He's the Sentinel-3, mainly on the thermal, the SLSTR program science leader at the University of Leicester. So if you visit the University of Leicester and you're interested in thermal, there's a nice group of people to meet. And it's with China Agricultural University and Peking University as well. So between this kind of triangle of activity, the kind of things we're trying to tackle are drought monitoring and crop yield estimates, because everyone's still talking about agri-tech. And I think in Russia we can think about forest tech. I think there's as much need to develop the technology around observing forests, especially under a warming climate, than there is over food security. I think I read last week 11,000 scientists have signed up to this climate emergency. And I think some of the technology that we'll need to monitor these forests systematically might arise from that. And then using Sentinel data to improve drought mapping and yield estimation. Again, it's trying to get this working together. So what we've done, this is particularly with Peking University, is to try and make sure the split window algorithm for the retrieval of land surface temperature over China is optimized. So Professor Huazhong Ren from Peking University spent some time. We sent some of his students over to Leicester, and we've now got an optimized LST retrieval product over these large areas of agricultural areas in China. Then what we've done with that, once we've got a good LST product, we can then combine that with Sentinel 3A NDVI. Yes, it gets a mention in every single presentation today. Sometimes I tell my students, read about the NDVI, and they say, yeah, but it's 1990s. I said, yeah, but it's still very important today. It tells us about what's going on, but combining vegetation health with temperature can really tell us a lot about the behavior of surfaces. And I think if we're going to characterize this kind of longer growing period, longer warming period, looking at land surface temperature, if that's possible, over these Russian forests and at these tree-line zones could be really valuable, combining that with the vegetation health. They've called this VTCI, the Vegetation Temperature Condition Index, which was an index that my colleague in China Agricultural University has been working on for a long time. So what we get is, over time, because these satellites are going over very frequently, is we get changing dynamics of the surface. And what the interest is, can we see drought? How long has the drought been? What might the drought, if it goes towards a warm edge, how might that affect the overall yield? And then some of the more interesting and very recent work, which just submitted this for review, is to kind of look at how we can then go from Sentinel 3, which is definitely not at the field scale, down to Sentinel 2, alongside, and again, compare that to MODIS. So maybe it's not so clear, but if we look at this Terra MODIS VTCI product, which looks very blocky, now we've fused that with Sentinel 2 data, so we can get the Sentinel 2 scale, and we get a much more finer scale outcome by combining these two through a fusion algorithm that this student, his name's not on there, is produced for a PhD. So the message for me is very clear. We've got multiple sources of satellite data that we're going to get into the future. We need to work really hard at methods to fuse them. We need to think about models to integrate. We've seen very interesting spatial and temporal patterns in the radar data, not radar backscatter, which is quite noisy, very speckly, affected by topography. But we've been looking more at coherence. And some interpretation of those signals will be really useful to do. And then the other thing this is where kind of geography computer science interfaces for me is, this is part of my learning curve, because again, when we collaborate with different organizations, we're always seeking things to actually understand. To me, it's this kind of concepts of neural networks, random forest, very much black boxes to me, because I'm from a school of geography, geology and the environment. A bit like Bob, thinking what's the process, what's happening on the ground surface, whereas some people are quite happy to just stick data through a neural network and keep their fingers crossed and hope for the best. And that's again why this interface between mathematics now, computer science, informatics, is actually really interesting. It's something we can't ignore. There's a lot of funding there to explore these digital solutions, and we very much look forward to doing that. And this is in fact, this is a student from China Agriculture University, and using this modified version of a neural network, the results have really moved forward. So there are some really nice tools, maybe sitting out there, developed by mathematicians, that will really help our understanding about vegetation dynamics. My last slide, just to really put out an advert. University of Leicester is really trying to transform its work around Earth observation and space. My colleagues in physics and astronomy, they've contributed to a mission that's been launched into space every year for the last 50 years. And they were part of the original ATSR instrument that looked at sea surface temperature. And so we're very interdisciplinary, but we don't work together. In fact, I probably spend more time in China than I do in the Department of Physics and Astronomy, which is 200 meters away from my office. So we're trying to co-locate. And this is a really exciting opportunity for international collaborations, because not only are we going to co-locate around Earth observation, we're going to co-locate around AI and low-cost satellite production, more upstream solutions, also low-cost access to space. And you'll notice this SME, the small to medium-sized enterprise. So there'll be some businesses there as well. And I have this role in the university. I'm the College of Science and Engineering Director of Enterprise and Knowledge Exchange. Now, goodness me, I've been doing it for 1 year, and I don't really understand completely what the job entails, but I think part of it is to kind of energize the kind of the industry around it. And I think part of that energy comes from producing products that people want to use and users are interested in developing and working, getting ideas and sharing ideas with business and so on. So this is a great opportunity, and we'll get the new building in 2021, and it's a good place to visit and start a discussion around visiting the University of Leicester and our network to other places in the UK through projects we've got with Bob and a few others. Of course, welcome to visit those organisations as well. So there's my email, and very happy to discuss with people afterwards. Thank you very much. Thank you.
Hello. So if I got it in the right way, you use the decision tree at the first. So why didn't you use the random forest? Decision tree is just overfit time over time.
Yeah, so we experimented with a number of, I guess, classification methodologies. I think the slide that we showed indicated decision trees, but we've moved on to random forest, and I think we also looked at support vector machines.
Yeah.
But we're still not. I think what we need to do is to look at more of a kind of physical coherence-based model, and try and parameterize that before we. And that might give us some clues about the kind of training data. Oh. We might actually refine some of the training data that we're using, and we also need to visit the field, because we get some nice RGB color composites. But I think we need to go into the field and see actually what's happening on the ground surface.
Oh, okay.
Yeah.
And also about programming. At first, what libraries did you use? Scikit-learn, or you programmed support vector machines and decision forest all by yourself?
No. I think we're using. Is it R?
Scripts? Okay. No,
yeah,
not Python.
Well, I think
R. Yeah.
You know, we had
it's a good
we debated for 3 hours a few months ago. Do we teach R or do we teach Python? I think we decided to teach both, because they're quite interrelated.
Yeah.
And so
data structure.
Yeah. We just find a solution on one of those platforms, no problem.
Okay, so thank you for answer.
Еще вопросы? Пожалуйста, да.
It's very interesting for us. but where is your materials will be published here and are very interesting for us. По-русски я могу еще сказать, что очень важно, что объяснены работа с Sentinel, аппаратурой, которая доступна, очень четко высказана краткость информации, поскольку она дорогая и так далее. И, значит, высокая точность. И, в общем, хотелось бы, чтобы этот материал был опубликован в нашей работе. Thank you very much.
I don't know, you don't have, no, so maybe a short translation, I don't. So, I mean the... Sorry? No, I mean because you did not get translation because of the... So it was just the wish, it was stressed that the Sentinel one is important because the data is available and I mean it's possible to use because it's free of charge. So, and it was this kind of suggestion to publish this result to make it available for everyone. Yeah. So, какие
I mean,
еще вопросы?
Sergey, some observation of Russian Earth observation satellites. Are people here using mainly NASA data sets, Sentinel, or is the kind of picture changing given other contributions?
There are different users. I mean, the users like us, so we are using MODIS and Sentinel and Landsat, and especially because for us it's very important to work with time series.
Yes.
So the Russian satellites, according to concept of Russian Space Agency, the main focus is for the moment, and the very high resolution data, which is difficult to use as a time series. So it means there are the number of users where the very high resolution is very important. I mean, they want to measure, I don't know, what kind of the cadastre, I don't know what, to measure areas so unfortunately, so for the moment we are using more NASA and ESA data, yeah. And mainly because of this reason, yeah. The time series is absolutely crucial for us. Yeah.
Thank you.
Еще есть вопросы? Ну что, спасибо.